Hey, what's up, guys? Yeah, so today is my new series, and I want to talk about analytic number theory. And I think this topic is very interesting, and I have been learning this topic for my own interest for a long time, maybe several months. And I want to prepare my own lecture and my own video just for fun and share with you guys. And I hope you guys subscribe to my channel. So the reference, I think the best reference is Terence Tao's blog. You just need to type the analytic number theory, and then there are several books that I remember that the Apostle has also a book called Analytic Number Theory. But basically, you call it analytic number theory, then you can see the several books, and then I think they are all very good. And I will post some reference that I think is very good. And I will basically, since it's introduction, so I think one can basically follow. There's a Harvard notes by 3.1 called the analytic number theory. Okay, so I think let me just write down. So I hope to, by the way, hope you guys subscribe to my channel. So I hope to introduce I think the idea is that, so I should talk about the standards elementary analytic number theory. So basically these topics that using, I will say that using calculus to bounds BU, O and D to bound the several arithmetic function. Okay, so arithmetic function are several functions that's related to number theory, like maybe the tau of n, the number of the factor of n, and the phi of n, which is Euler function, and also some function which is related to the prime number theory. Okay. And the next I should say is that yeah, so this is the only using calculus, and I think the technique is really standard analysis. I guess if you learn the advanced calculus, it should be very easier. Should be very easy. And the next is that the complex analysis version. So if you use the complex analysis, then you can prove the prime number theorem, and also you can understand some Riemann conjecture, and also some L functions and the character. Okay, and this is one thing I want to introduce. And also there are two types of analytic number theory. I think the Territals have introduced this one. So one is called the additive analytic number theory. Basically ask that the prime number problem. So for example, the famous Goldbach conjecture. Every prime greater than 2 can be equal to sum of the two primes. Sorry, every even greater than 2 can be equal to the sum of two primes. And the multiplicative prime number theory. So this is also this is somehow the reflected nature of the prime number. So usually one have some prime number theorem, and also the distribution of primes. Yeah, this is all very interesting. So I want to introduce some of them and provide a simple picture of the analytic number theory. And I will most focus on all this. Okay, I will definitely prove some of this, and I will go through all of this, and talk what I know and what I learned. Okay, hope you guys subscribe to my channel. So let's start. So today should be very easy. So I just want to say the fundamental theorem of the arithmetic. So prime and I should say trivial zero, prime and fundamental theorem of arithmetic. Okay, so I think one knows about divisibility of prime, divisibility and prime. I think this is a very simple. So the idea is that given there's just definition, right? So given a non-zero integer and n, and then we say the we say D divides N. So notation is this, means that there is this M such that there is this M such that N is dm, right? Okay. So this is notation. Okay, and very simple exercise is at D1, D2, D2, D3, and you can prove that D1, D3. Okay, so this is trivial. Okay, and zero cannot be okay. So, zero you cannot zero cannot put here, right? So this is very important. You cannot divide zero. Okay. Okay, and one can define a GCD, the greatest common divisor. I think it's very simple. So GCD is denoted by, let's say, given any two integers, both non-zero. So let's say A non-zero, B non-zero. So given any two of them, one can define the greatest common divisor to be the first satisfied, is a number satisfy the first condition, such which is positive. So let me just write down GCD of AB is the positive integer. Let's say such that D divides A and the D divides B, and then you take the minimum. So this guy is a positive integer, right? So every positive integer must have the minimum, right? So you can take a set, you can take a minimum. Or basically another definition is that satisfy one, and two is that if C divides A and C divides B, then D divides C. Okay, so you can also define GCD AB to be the number which satisfy these properties 1 and 2. Okay, and if you assume that greater or equal to 0, then this kind of number is unique. Okay, the reason is that if there's another one, then the D1 will, then you can use this property to prove that this is unique. Okay, and you can also define the least common multiple. This is LCM, and this guy is also easy to define, right? So you can say that the unique. So this is the unique integer, the unique integer M, such that the first one is that A divides M, B divides M, so it's a multiple of both, and the minimum, right? So if A divides N and B divides N, then M must divide N. Okay, so it's similar to GCD. Another simple exercise is that GCD AB times LCM AB is the same as A times B. Okay, so I don't want to prove this, but then let's check some example. Maybe A is 12, B is 18. Right, so what is the greatest common divisor? 6, right? And what is LCM? AB, right? So 24, 36. Right, hopefully 36 is correct, right? So you can times these times. These two times should be the same as these two times. Yeah. Really? Let's check. So 12, right? So 2 times 8 is 16, 8, 9, 1. Right, so it's 200 this, and yeah, correct, right? Okay. Okay, so let's define price. It looks stupid. So if an integer, if a positive integer, now 1 is prime and is 1, so definition is that so if actually if n is greater than 1 and n is called prime, if there's no if only the positive, so if only divisor of n is 1 and itself. Okay, so divisor is restricted to greater than 0. Okay, so that means this guy can only have factor 1 or 0. So this means that n can only be right than 1 times n or n times 1 if every term need to be positive. Okay, so example that 2, 3, 5, 7, 11, 13. Woo. Okay. And okay, so now that's it. So let me just write down the theorem that I will not prove. I think this is the simple you should prove in the algebra course. So fundamental theorem. of arithmetic. Okay, so basically the theorem is that so every integer greater than 1 can be written as the unique product of primes. I should say up to permutation. Okay, the reason I don't want to prove, but this is you should prove in algebra, or you can see my proof I will post my algebra video. But basically the reason is just say that one sentence is that the integer is a UFD. The reason is that the integer is a PID, right? So the integer is a principal ideal domain, and the principal ideal domain will imply a unique factorization domain. So each unique factorization in the irreducible element, in this case, is just the integer prime number. So every prime number, every number can be written as unique product of primes up to permutation. Okay, so one can just write n into P1K1, P2K2, up to Pn Kn, such that all our Pi are distinct. Distinct. And the Pi are prime. And the Ki are greater or equal to 1. Okay. So this is like a very elementary, very elementary results. Ooh. Okay, so let me just write carefully. Okay, so this theorem is that the final theorem I want to prove, which is very old, but we want to prove in an analytical fashion. Okay, and this guy has at least 3 proofs. Okay, but let me just write down analytical proof that I think is very interesting. Okay, so the very famous, they're infinite primes. Okay, this is very old. Okay, so I think back to 2000 years ago. Okay, so the first proof that really famous is it's come from the Egyptian mathematician. So basically, you can assume that your prime is 2, 3, 5 terminate on some p, right? And then you can define n to be 2, 3, 5 up to b plus 1, right? So n should be so p is the largest prime, right? So but n is equal to 1 modulo any p, right? Modulo any p. So any p I, right? So contradiction, right? Because n should be a composite number. Oh, by the way, the composite number is a number which is not prime. Okay, so n should be a composite number because n should be composite number, but n is not divisible by any prime. Okay, so contradiction. Okay, but this kind of proof is very difficult to extend, right? So this is why analytical number theory come from, because this kind of proof is very genius, but cannot easy to extend. Okay, the second proof is that if you know the zeta function, which zeta s defined to be this, and then you can prove that zeta 1 is infinity, and then start from this you take a log, and then you can prove 1 over summation of primes will be infinity. Then this you prove that they're infinite primes. Okay, so this kind of proof is very powerful because it related to this. It actually proved more powerful results such that the 1 over p is converge. And once you use 1 over p converge, then you can easily prove that they're infinite primes, right? Otherwise, that if they're a finite primes, then the least sum will converge. Okay, and then there are third argument that I will talk in the future, or I may already talk about in some previous video. Basically, is the density argument. Okay, so this is this is like I would say this is more combinatorics way. Okay, so I will list the proof. I will give this video the proof for this video below. So if you're interested, you can go to. Okay, so what I want to do is the third proof, the fourth proof, which is analytical way. Okay, this is really weird, right? It's probably simple. Like who cares? Okay, but let's prove this by unique the way. Okay, let's prove it by analytical fashion. So one simple notation that we will use in the analytic combinatorics, I call this n means that the set of, I should say the set of 1 to 2 up to n. Okay, so it's a set of from 1 to n. Okay. Okay. So let me just write down. So I also define a n. Let's define a set, which this set is very stupid. It says called npx. P is not important, right? But let's just write down just submit the number of the n belongs to let's call it this is stupid, right? So n belongs to n such that n is equal to x, right? This is just exactly x. Okay. Okay. So let's see how should I bound this x if I know primes. Okay. So the proof it really looks very interesting, right? Because I can write npx in terms of the unique factorization, right? So I know UFD. So I know that I can write these guys a tuple, right? Like a1 up to ak, and p1a1, pk less or equal to x. And my notation must enforce that all the a1, ai are greater or equal to 1. Okay. So this is the factor. This is the, you can write npx as a tuple of each possible factor number on these primes, such that all the p1 u up to pk greater or equal to x. And then your pk, and then your p1, p2, pk belongs to a set of all prime. Okay, I use this set of all primes. Okay. So this is just another representation of NLP of x. Okay, so let's look this, right? So this NP, let me just write it again. Just A1, A2 up to AK, and all the AI is integer, and P1, A1 up to PK, AK. Less or equal to x, right? So you can take a log. Okay, so this means that the a1 log p1 up to ak log pk less or equal to log x. Okay, so that means what? Then these are all positive, right? So that means particular ai will less or equal to log x divided by log pi, right? But log pi is less or greater or equal to log 2, right? So these guys, the log x log 2. Right, it's very stupid. Okay, and then you can choose every a1, right, to be let's say you total have k primes, right, p1 up to pk, right, to k primes. Okay, so the np of x will less or equal to what? The k log x divided by 2 log k to a k, right? There may be plus 1 or something, but it's not important, right? Asymptotically, npx is less or equal to log x divided by log 2k. Okay. So I can write it as 1 over log 2 to the power k log x to k. Okay, and sorry. Let's see. So AI can less or equal to this, right? So I can replace each AI as this, and yeah, and let's see. Right. So yeah, this is So almost look like this, right? So asymptotically just 1 over log 2k log x. Okay. So the idea is that if there is only finite primes, right? So as x large enough, right? Suppose there are only finite primes, right? So there will be largest prime, that's k p here, and then the k can be arbitrarily large. K already very large, right? Maybe k may be some finite term because they're only finite. And then now you choose x, which is greater than k, right? So k is large enough. Then if k is large enough, then these terms is a constant, right? Because k already fixed. So np of x is equal to some finite term, which is some constant, times log x to the power k. Okay, k is some power, right? But np of x is what? It's just x, right? So the x can be now x, right? X is less or equal to c times log x to the k. Okay, so this is a contradiction. Okay, the reason is that if for some constant this term is true for large enough x, then I can shift it in terms of this. I can shift it become this, right? But log x to the k divided by x goes to 0 as x goes to infinity, right? So c times 0 equals 0 greater or equal to 1. Impossible. Okay, so nonsense. Contradiction. Nice. Okay, so which proves that there cannot be finite primes. Okay, so this is the analytical fashion to prove this. And then in next video, then I will introduce some elementary number theory function, and we can start analytic number theory journey. Hope you guys subscribe to my channel.